far beyond the last major planets, beyond the broad sweep of the Kuiper Belt, beyond the region where sunlight still feels in some way like the sun's domain. Voyager 1 moves through a part of space that no earlier human machine had entered. It is not heading toward a nearby star in any practical sense. It is not approaching a destination that can be reached within a human lifetime or even within many thousands of years. It is simply continuing outward, carried by the momentum given to it in the late 1970s, moving through a dark environment where the usual landmarks of the solar system have thinned almost to nothing. This is interstellar space, though even that phrase benefits from care. It does not mean a crowded place between bright stars. It does not mean a region filled with dramatic clouds and visible structures. In the local sense, it means a very sparse medium outside the main bubble inflated by the sun. That bubble, called the heliosphere, is formed by the solar wind, a flow of charged particles streaming outward from the sun in all directions. For a very long time, Voyager 1 travels inside that influence. Then, after decades of motion, it reaches the boundary where the outward pressure of the solar wind can no longer dominate the material beyond. Crossing that border does not bring the spacecraft into a new world of dense matter or sudden brightness. It brings it into a quieter, thinner, more difficult reality, one defined less by what appears and more by what can barely be measured. The darkness there is not absolute, because space is never truly empty. There are magnetic fields, fast particles, traces of gas, and the continuing passage of light from distant stars. But compared with the inner solar system, it is a place of remarkable emptiness. The sun is still visible from there, but it is reduced to one bright star among many, though brighter than the rest. Its warmth is functionally gone. Its light is too weak to matter for power. Its gravity still extends outward, because gravity has no edge in the simple sense, yet gravity is not the same as environment. Voyager 1 remains gravitationally tied to the sun, while no longer immersed in the sun's wind-dominated region. That distinction matters because it reveals how space is organized. The solar system is not just planets in orbit. It is also a volume shaped by invisible flows, by pressure, by fields, by plasma, by the competition between what streams outward from a star and what already exists in the galaxy around it. Voyager 1 has become the instrument that lets scientists examine that difference directly. From Earth, interstellar space had long been studied indirectly through theory telescopes and the behavior of cosmic rays. Voyager 1 adds something rarer. It carries instruments into the region itself. It senses changes in particle populations, changes in magnetic conditions, changes in plasma behavior. It does not see this frontier in the familiar human way. It measures it. And from those measurements, a picture forms slowly, carefully, with less drama than popular language often prefers. What emerges is not a sharp wall, but a transition zone, a place where one environment yields to another. This makes Voyager 1's location scientifically precious, but it also makes it emotionally striking. The spacecraft is a machine from another era, still active in a region that was once entirely abstract to human experience. It was built when room-sized computers were common, when memory was scarce, when engineering margins were physical and conservative. Yet that machine now operates in a place so remote that signals take many hours to move between spacecraft and Earth. The delay itself becomes part of the environment. Nothing happens quickly there from a human perspective. Every action is stretched by distance. Every correction requires patience. Every data point arrives from a past moment already gone. This gives Voyager 1 a peculiar presence. It is active but always distant in time as well as space. It can be imagined only through numbers, radio transmissions, engineering readouts, and the discipline of interpretation. There is no camera view guiding the mission now, no cinematic window. The reality comes through telemetry, through changes in counts and rates and voltages, through the behavior of systems that continue to function long after their planned prime. In this sense, the far frontier is both physical and mental. It tests instruments, but it also tests language. Words like empty, silent, distant, and cold are all correct, yet none fully captures the scale involved. Distance on Earth is usually experienced through travel time maps, fuel terrain. Distance in deep space loses those familiar references. It becomes almost resistant to intuition. Voyager 1 is more than 15 billion miles from Earth, a number so large that it tends to flatten in the mind unless unpacked slowly. A radio signal moving at the speed of light still requires well over 20 hours to arrive one way. No vehicle humans have built can go there and return in any meaningful operational sense. No repair crew can follow. No rescue is possible. The spacecraft survives by being sufficient unto itself, a small autonomous presence in a place where intervention is measured in radio commands and long waits. And yet, it remains connected. That is the central wonder of this frontier. The machine is not lost. It is not merely drifting as dead hardware through the galactic dark. It is still in relationship with Earth. It still reports. It still responds. It still turns an unimaginably remote region into something known a little better than before. The far dark frontier is therefore not only a location beyond the heliosphere. It is a continuing experiment in connection across scale, across delay, across fading power and vast emptiness. Voyager 1 moves through a region where the Sun's direct environmental rule has ended. And in doing so, it reveals that the boundary of the human world is not where human bodies can go. It is where human instruments can remain meaningful. Out there in the thin medium between stars, a small craft from 1977 continues onward, carrying with it the quiet extension of human attention into the dark. The connection between Voyager 1 and Earth exists as a radio link so delicate that it almost seems implausible. By the time the signal arrives, it is unimaginably weak spread across distance so vast that the original transmission has thinned into a trace barely distinguishable from the background noise of the universe and the electronics used to receive it. Yet it arrives in a form that can still be detected, measured, and translated into meaning. This is not because the signal remains strong in any ordinary sense. It does not. It is because every part of the system, from the spacecraft transmitter to the receiving antennas on Earth, is designed around patience, sensitivity, and the disciplined handling of faint information. Voyager 1 does not send a powerful broadcast across space like a beacon flooding the dark. It sends a narrow, carefully aimed stream of radio energy. The spacecraft directs that transmission through its high-gain antenna, a dish built to focus radio waves into a tighter beam than would otherwise be possible. Even so, the beam expands over distance. It cannot remain pencil-thin across billions of miles. As it travels outward from the spacecraft, it covers a larger and larger area, and the energy it carries becomes spread over that expanding front. What reaches Earth is only a tiny fraction of what left the spacecraft. Most of the beam passes into space beyond the planet, continuing onward. Earth intercepts only a minute share, and only when the geometry is right and the receiving system is ready to listen with extraordinary care. Radio waves are part of the electromagnetic spectrum, like visible light, but with much longer wavelengths. They travel through the vacuum of space at the speed of light, and unlike a physical object, they do not need matter to carry them. This makes them suitable for communication over interplanetary and interstellar distances. But suitability does not mean ease. Every communication system faces the same basic problem. A signal must remain recognizable after traveling through an environment that adds uncertainty. In deep space, the environment is not crowded with weather buildings or ordinary interference, yet the challenge is still severe because of sheer distance. The farther a signal travels, the weaker it becomes at any one receiving location, simply because it spreads. This is one of the fundamental facts governing space communication. It is not a flaw in the spacecraft or the antennas. It is a property of geometry. Distance dilutes concentration. The result is that by the time Voyager 1's signal reaches Earth, it is far below the level of anything humans can sense directly. No ear could hear it. No simple receiver could pull it from the noise. It must be collected over time, amplified with exceptional care, and processed with methods designed for near-vanishing information. The very idea of noise becomes important here. Noise is any unwanted variation that mixes with the desired signal. Some noise comes from the receiving equipment itself, because all electronics have thermal motion and limitations. Some comes from the sky, from cosmic sources that emit radio energy. Some comes from Earth's own environment. The problem is not merely that the signal is weak. It is that weakness and noise begin to resemble each other. To recover, meaning engineers must build systems that preserve the structure of the incoming transmission without drowning it in the very act of trying to hear it. This is why low-noise amplifiers matter so much. They strengthen the received signal while adding as little extra uncertainty as possible. This is also why long integration times and careful signal processing are essential. The receiver does not simply notice a burst and declare success. It accumulates evidence. It distinguishes pattern from randomness. It locks onto a known frequency and tracks small changes caused by motion between Earth and spacecraft. Those changes arise from the Doppler effect, the same basic principle that alters the apparent pitch of a passing siren. In radio communication, motion can shift the frequency of the signal slightly higher or lower. Since Earth rotates and orbits the Sun and Voyager, one moves through space, the receiving system must account for this continuous change. To listen successfully is therefore not a passive act. It is an active correction process, a form of alignment performed in mathematics and electronics. The signal itself carries more than one kind of importance. Part of it contains engineering telemetry information about the spacecraft's health. Voltages, temperatures, system states, and instrument conditions can all be represented within this thin stream of radio energy. Part of it may carry scientific data encoded measurements from the instruments still operating. Part of it also reflects the stability of the spacecraft as a pointing platform. If the antenna is not aimed accurately enough, the signal can weaken further or vanish into non-detection. Voyager 1 must therefore maintain orientation with care. A spacecraft that is silent is not always broken in the dramatic sense. It may simply be misaligned by an amount tiny in angle, yet immense in consequence across deep space. This reveals how fragile the entire chain is. Communication depends on power antenna, pointing transmitter, health frequency, stability, receiving sensitivity, and the ability of Earth-based systems to extract order from almost nothing. The miracle is not that one heroic machine shouts across the galaxy. The miracle is that every piece of the chain functions with enough precision to let a whisper survive. That whisper is not continuous in the human sense of a spoken voice. It is structured digital, limited by low data rates that reflect the physical reality of deep space communication. There is no abundance in this link. Every bit is costly. Every transmission is shaped by the need to fit useful information into a channel of narrow capacity. Yet within that narrowness, an entire relationship persists. Commands leave Earth travel for many hours and reach the spacecraft as patterns of radio energy. Responses return in the same patient way. The spacecraft and the ground do not converse quickly. They exchange carefully prepared statements across an almost unimaginable gap. This changes the emotional scale of communication itself. On Earth, communication is usually associated with immediacy. Messages are sent and received in seconds or less. Delay is treated as inconvenience. With Voyager, one delay is foundational. A one-way light time of more than 20 hours means that every interaction belongs to a slower world. There is no rapid correction, no instant clarification, no direct intervention. Human intention must be translated into commands sent into darkness and trusted to arrive. Then the waiting begins. When a reply comes back, it is evidence from the past, a report from a spacecraft, as it was nearly a day earlier. This does not weaken the connection. In some ways, it deepens it. The link becomes a disciplined act of faith in physics, engineering, and repetition. A faint signal crosses emptiness, because radio waves obey reliable laws, because antennas can be pointed with extraordinary precision, because noise can be managed, though never eliminated, and because patient minds on Earth continue to listen. The vast distance does not erase communication. It transforms communication into one of the most exacting forms of attention human beings have ever sustained. The signal from Voyager 1 does not arrive at a single waiting dish standing alone under an open sky. It arrives within a coordinated listening system built across the rotating Earth, a system designed so that deep space missions can remain in contact even as the planet turns. This system is the Deep Space Network, a distributed arrangement of large radio antennas, receivers, transmitters, timing systems, control rooms, and engineering practices that together make distant communication possible. Without it, Voyager 1 would still be traveling through interstellar space, but it would no longer be part of an active mission. The spacecraft would continue as an object. The mission would end as a relationship. The Deep Space Network preserves that relationship by turning Earth itself into a listening instrument. Its sites are placed far apart in longitude, roughly spaced around the globe, so that as Earth rotates, one complex can take over from another and keep a deep space spacecraft above the horizon for communication. This arrangement allows nearly continuous coverage for missions that move too far away to tolerate long daily silences. For Voyager, one whose transmissions are so weak and whose situation requires careful tracking, this continuity matters deeply. A break in visibility is not merely an inconvenience, it is a narrowing of opportunity. Every communication window is valuable because commands and telemetry must travel across such long delays that efficient use of contact time becomes essential. The Deep Space Network is therefore not simply a set of antennas. It is a schedule, a choreography, a way of managing planetary rotation so that human attention can remain extended into deep space. At the heart of the network are very large dish antennas. Their great size is not for spectacle. It is a direct response to physics. A larger collecting area allows more of the incoming radio energy to be captured, which improves the ability to detect faint signals. When Voyager 1 speaks across billions of miles, the amount of energy that reaches Earth is minuscule. A small antenna would collect too little. A large dish gathers more of the wavefront and concentrates it at a receiver, giving the signal a better chance of standing above the noise. The shape of the dish matters too. It is a paraboloid, a curved surface that reflects incoming radio waves toward a focal point where the receiving electronics are placed. This geometry allows weak parallel waves from a distant source to be brought together with precision. The antenna must then be pointed with extraordinary care. Although the sky is vast, the beam from a large dish is relatively narrow, and Voyager 1 occupies only a tiny apparent position within that sky. To receive the signal well, the dish must track that position, continuously compensating for Earth's rotation and for the changing geometry between planet and spacecraft. The act of listening becomes mechanical and mathematical at once. Motors move immense structures with careful smoothness. Software predicts where the spacecraft should appear. Controllers refine pointing and confirm lock. Everything depends on precision carried out steadily over long periods. The network does not only receive, it also transmits commands outward, and transmission brings its own demands. To send a command to Voyager 1 is to launch a stream of radio energy that must remain coherent, correctly encoded, and accurately aimed for a journey of more than 20 hours one way. High transmission power helps, but power alone is not enough. Stability is just as important. The frequency must be controlled, the timing must be exact, and the command structure must be reliable, because the spacecraft cannot ask for immediate clarification. Once sent, a command enters the long silence between worlds. For this reason, the deep space network depends on exceptional timing standards. Time in ordinary life is often loose-rounded to convenience. In deep space communication, it becomes exacting. Receivers must know when and where to expect a signal. Tracking systems must measure frequency shifts with high precision. Ranging and navigation depend on accurate timing, and even small errors can matter when extended across billions of miles. The network therefore relies on highly stable clocks and disciplined synchronization practices that keep its operations anchored to repeatable standards. Time in this context is not just a way of organizing work, it is part of the instrument. Another essential part of the network is its ability to adapt receiving methods to the difficulty of the target. Not all spacecraft are equally hard to hear. A mission near Earth or even near Mars presents very different demands from a probe at the edge of the Sun's influence or beyond it. Voyager 1 belongs to the extreme end of this range. Its signal is faint enough that the network may use long observation periods, careful frequency prediction, specialized signal processing, and in some cases combinations of resources to improve reception. Engineers think in terms of signal-to-noise ratio, link margin, antenna gain, and data rate. But beneath these technical ideas lies a simpler truth. To hear something this remote, the network must reduce every unnecessary source of loss and make full use of every available advantage. It is listening at the edge of what careful engineering can sustain. The Deep Space Network also carries the weight of history. It was built to support many missions across decades, adapting as exploration expanded from the Moon to planets, comets, asteroids, and the deep frontier beyond the outer planets. Voyager 1 is one of the clearest demonstrations of why such a network matters. A spacecraft launched in the 1970s continues to return useful information because the ground system has remained capable, maintained, and improved. The relationship between spacecraft and Earth is never only about what flies. It is equally about what stays home and keeps listening. Massive antennas, standing in remote places on Earth, form the other half of the mission though they do not travel through space themselves. Their stillness is what makes the distant motion meaningful. They are the fixed ears that allow the moving craft to remain present in human knowledge. There is also an almost quiet humility in the way the network works. It does not conquer distance by force. It manages distance through accumulation, patience, and precision. It gathers tiny amounts of energy. It filters noise. It tracks predictable shifts. It schedules handoffs from one part of Earth to another. It turns a spinning planet into a persistent observer. In doing so, it makes communication with Voyager one less like a dramatic shout across the void and more like a long practice of sustained attention. The spacecraft is unimaginably far away, but the network makes that fact operational rather than merely poetic. It transforms remoteness into a solvable engineering problem, never easy and never fully relaxed, yet still tractable through discipline. As Earth turns beneath the sky, one antenna complex yields to another, and the listening continues. Through that continuity, Voyager 1 remains audible. Through that audibility, interstellar space remains not only a distant concept, but an active place from which data still returns. The radio link between Voyager 1 and Earth is not meaningful merely because energy arrives. Meaning appears only when structured information survives the journey. A faint carrier wave by itself could confirm that the spacecraft still transmits, but it would reveal very little about the condition of the machine or the scientific environment through which it moves. To become useful, the transmission must contain organized changes that represent data. This is the language of radio communication. In its operational sense, not a language of words or grammar, but a language of patterns, timing, coding, and interpretation. Voyager 1 does not speak in sentences. It sends measured variations that can be recognized by receiving systems and converted into engineering values, scientific readings, and command responses. That process begins with the most basic unit of digital information, the bit. A bit represents one of two possible states, a simple distinction such as yes or no, on or off, 1 or 0. Modern life is saturated with digital systems, so the idea can seem ordinary, but across interstellar distance, it takes on a different character. Each bit transmitted by Voyager 1 must survive a journey in which the signal weakens almost beyond comprehension. The bits do not travel as tiny labeled objects. They are embedded in changes imposed on a radio wave. In broad terms, the spacecraft alters some property of the transmission in a controlled way so that the receiver can detect a sequence. That sequence is then interpreted according to agreed rules, already known to both spacecraft and ground systems. Communication depends on this shared structure. Without it, the incoming signal would be only an oscillation buried in noise. With it, the signal becomes readable. The idea of data rate follows naturally from this. Data rate is the speed at which information is transmitted, usually measured as bits per second. For Voyager 1, the data rate is extremely low by ordinary standards, not because engineers failed to imagine something faster, but because distance imposes hard limits. A weak signal cannot reliably carry large amounts of information quickly unless the receiving conditions are extraordinarily favorable. To force too much information into too little signal strength would invite confusion between the message and the noise. The result would be lost accuracy, higher error rates, and possible failure to recover the data at all. This is why deep space communication often accepts slowness in exchange for reliability. A lower data rate gives the receiver a better chance to distinguish intentional structure from random fluctuation. It is a trade that reflects the physical reality of the channel. In this sense, slowness is not inefficiency. It is a method of survival. The receiver on Earth does not merely notice whether a signal exists. It must determine exactly how the signal has been modulated, meaning how the information has been impressed onto the radio wave. Different systems can use different modulation strategies, but the principle remains the same. Some controlled feature of the wave is varied according to the data being sent. The receiver then compares the incoming pattern against expected possibilities and reconstructs the original bit stream. This reconstruction is never performed in a perfect void. Noise is always present. The question is whether the intended structure remains strong enough or consistent enough to be recognized despite that noise. This is where error control becomes essential. In any long and difficult transmission path, some bits may be received incorrectly. A random fluctuation can make a 1 appear more like a 0 or blur the distinction altogether. If every bit had to arrive perfectly on the first attempt with no redundancy, deep space communication would be far more fragile. Error control coding helps solve this by adding carefully designed extra information to the transmission. This added structure allows the receiver to detect and in some cases correct certain errors without needing the message to be sent again. Redundancy in ordinary language may sound wasteful, but in communication theory, it is a source of resilience. The transmitter sacrifices some efficiency in order to increase the chance that the original message can still be recovered after damage by noise. In Voyager 1's case, this principle is not a luxury. It is one of the reasons the mission can function across immense distance. There is also a distinction between raw bits and interpreted information. A received sequence does not automatically announce its own meaning. Ground systems must know how to parse it, how to divide the stream into recognizable units, how to identify which portions refer to temperature, voltage, instrument status, scientific counts, or housekeeping data. Telemetry. The reporting of spacecraft condition depends on this mapping. A particular pattern corresponds to a particular sensor reading or system state. Once decoded, it can be turned into numbers engineers understand. A value representing onboard temperature is no longer just a pattern of bits. It becomes a clue about thermal health. A value representing power level becomes a clue about electrical margin. Scientific data works in a similar way. The instruments record events or conditions, encode them according to mission design, and send them home through the same narrow communication pathway. Meaning therefore exists in layers. First, the radio wave must be detected. Then the modulation must be recognized. Then the bit stream must be reconstructed. Then the coded structure must be interpreted. Then the resulting values must be understood in physical context. At every stage, mistakes are possible, and so every stage requires design verification and care. The language of radio is thus less like a spoken exchange and more like a long chain of disciplined transformations. A physical wave becomes a measurable signal. A signal becomes a sequence becomes data. Data becomes knowledge. None of this would matter if the spacecraft were free to improvise, but it is not. The spacecraft and the ground are bound by fixed systems, by protocols decided in advance and preserved over decades. This creates another remarkable feature of Voyager 1's mission. The language still in use is rooted in engineering choices made in the 1970s, maintained through continuity of documentation expertise and patient operational memory. Even as ground technology evolves, the mission must remain able to understand the old machine on its own terms. This continuity is a quiet triumph. It means that communication is sustained not only by electronics, but by institutional memory and technical stewardship. To hear Voyager 1 is one achievement. To understand what it says is another. The message is small, slow, and vulnerable to corruption, yet it remains intelligible because the system was built with layered protections against confusion. Noise has not been defeated. It never is. It has been managed, limited, and outworked. Through coding, low data rates, precise reception, and careful decoding, order persists within weakness. That persistence is the real language of radio at interstellar distance. It is not fluent in the human sense. It is sparse, exact, and patient. But within that narrow stream, a spacecraft billions of miles away can still report its state returns scientific measurements and remain connected to the minds that continue to listen. Voyager 1 is often described through the scale of its distance or the endurance of its mission, but its continued existence depends just as much on something quieter and more concrete. It depends on the kind of machine it was at the beginning. Long before it became an artifact in interstellar space, it was a product of a very specific engineering culture, one shaped by the limits and habits of the 1970s. Those limits mattered. Computing power was modest, memory was scarce, components were less compact than those of later decades, and every design choice had to respect the realities of launch, stress, radiation exposure, thermal extremes, and the impossibility of repair once the spacecraft departed Earth. This did not produce a machine built for elegance in the modern consumer sense. It produced a machine built for resilience, with systems designed to do a limited set of tasks reliably under punishing conditions. That original character remains present in Voyager 1 even now. The spacecraft is not alive in the biological sense, yet it endures because it was designed with a kind of mechanical discipline. Its body is organized around a central structure that supports instruments, communications, equipment, propulsion elements, computers, and the long booms that hold certain sensors away from the main bus. The structure must do several things at once. It must survive, launch vibration, preserve alignment for key systems, and remain stable across wide temperature ranges. Unlike a structure on Earth, it cannot rely on routine inspection or tightening. It must hold its shape simply because it was built to do so. The high-gain antenna dominates the appearance of the spacecraft, a large dish that serves as both a communications tool and a symbolic face turned back toward Earth. But behind that familiar feature lies a more complex organism of subsystems, each with its own role and each dependent on the others. Power must be generated and distributed. Attitude, meaning orientation in space, must be sensed and controlled. Data must be processed, stored briefly, formatted, and transmitted. Instruments must be supplied with what they need while the spacecraft maintains thermal balance and operational stability. No single part alone explains longevity. Endurance emerges from the interaction of many parts that were designed not for luxury, but for margin. Margin is one of the most important ideas in spacecraft engineering. It means providing room between normal operation and failure, room for uncertainty, room for degradation, room for things to be worse than expected. In a mission that might last a few years, margin is already important. In a mission that stretches across decades, it becomes almost a philosophy. Voyager 1 benefits from this philosophy. Its systems are not infinitely robust, and many have aged or been turned off, but they were not built on the assumption that every condition would remain ideal. They were built with the knowledge that spaceflight punishes optimism when optimism replaces caution. This can be seen in the use of redundant systems for certain essential functions. Redundancy means having more than one path to accomplish a task so that a single failure does not automatically end the mission. Redundancy is not complete in every part of a spacecraft, because mass and complexity impose their own costs, but in critical areas, it can preserve capability long after individual components weaken or fail. Another feature of that engineering era was clarity of purpose. Voyager 1 was not a general platform expected to reinvent itself endlessly. It had a mission architecture with defined scientific goals, defined flight dynamics, and defined operational logic. That clarity allowed its designers to optimize for real needs rather than for fashionable possibilities. The spacecraft needed to survive a long journey, execute planetary flybys point instruments, and antenna accurately communicate over increasing distance and function with extremely limited onboard computing resources. From those requirements came a design that now appears almost austere. The computers are simple by modern standards. Their memory is tiny compared with even ordinary contemporary devices. Their logic is specialized. Yet simplicity, when paired with careful design, can become a strength. Fewer functions can mean fewer opportunities for uncontrolled behavior. Limited resources can force cleaner priorities. What the spacecraft lacks in flexibility, it partly gains in determinacy. It behaves according to systems that engineers can still reason about because those systems were constrained from the outset. Thermal design also belongs to this story. Space is often imagined as simply cold, but thermal control in spacecraft is not a matter of exposing a machine to one uniform low temperature. Different surfaces gain or lose heat differently. Electronics generate heat internally. Sunlight changes with distance and angle. Instruments and power sources create local thermal conditions that must be managed if components are to remain within survivable ranges. Voyager 1, therefore, depends on insulation, internal heat flow louvers, and radiative surfaces, and operating decisions that preserve warmth where possible. The fact that some onboard heat is produced by the power source becomes especially important in later decades when every watt has multiple meanings. Heat can be useful as well as dangerous. To stay alive in deep space, the spacecraft must keep some parts from becoming too cold to function. The design of the propulsion and attitude control system also reflects long-range thinking. Small thrusters allow Voyager 1 to maintain orientation, correcting its position so the antenna remains pointed toward Earth and the instruments remain properly aligned. These thrusters use finite propellant, which means every maneuver matters. The mission could not depend on wasteful control logic. It required measured, efficient use of resources over timescales, far beyond what many original mission plans would have treated as active life. Yet, because the underlying system was sound and the operations disciplined, that resource has lasted with extraordinary effect. Radiation tolerance is another quiet factor. Spacecraft electronics must endure charged particles and energetic events that can damage or disrupt circuits. In the 1970s, this challenge was already understood, though not with the modern language of hardened microelectronics as commonly used today. Voyager 1's electronics and architecture were nevertheless prepared for a hostile environment through conservative design shielding in appropriate places and operational practices that reduced vulnerability. This does not make the spacecraft invulnerable. It means only that it was never fragile in the casual sense. Its survival is not an accident of luck alone, though luck always plays some role in long missions. It is the result of a machine built by people who expected space to be unforgiving. There is a tendency in modern imagination to equate old technology with inferiority in every respect. Voyager 1 complicates that instinct. Its systems are old, but old does not always mean careless or crude. In this case, old often means understandable, robust, and designed with tangible physical margins. The spacecraft is a reminder that longevity can come from disciplined engineering rather than from complexity alone. Built in the 1970s, it carries the assumptions of that era into a place its builders could scarcely expect to monitor in real time half a century later. Yet those assumptions have proved unexpectedly durable. A machine once meant to cross the outer planets now continues through interstellar space, not because it transcended engineering, but because engineering at its best prepared it to remain useful long after its first horizon had passed. Voyager 1 continues to function in deep space because it carries its own long-lived source of electricity, a system very different from the solar panels that support many spacecraft operating closer to the Sun. At the vast distance where Voyager 1 now travels, sunlight is far too weak to provide useful power through ordinary photovoltaic methods. The spacecraft therefore depends on radioisotope thermoelectric generators, often referred to as RTGs, devices that convert heat from radioactive decay into electricity. This design makes the mission possible in the outer solar system and beyond, but it also introduces one of the central constraints that now shapes every remaining year of operation. The power source is steady in one sense and steadily declining in another. It does not shut off suddenly like an exhausted battery. Instead, it fades gradually as the radioactive material produces less heat over time and as the conversion system itself ages. Understanding this slow decline is essential to understanding why Voyager 1 still lives, why its remaining life is limited, and why every watt aboard the spacecraft carries extraordinary importance. The principle behind an RTG is both simple and profound. Certain radioactive materials release energy naturally as they decay into other forms. This process is not chemical burning. It does not require oxygen flame or any external trigger. It is a nuclear process in which unstable atomic nuclei transform and release energy, much of it as heat. In Voyager 1's case, that heat comes from plutonium, in a form chosen for its suitability as a long-duration source. The heat does not drive a turbine or an engine with moving parts. Instead, it is converted directly into electricity through thermoelectric devices. These devices rely on a physical effect in which a temperature difference across certain materials can generate an electric voltage. One side is kept hot by the decaying radioactive fuel. The other side is allowed to remain cooler by radiating heat into space. As long as there is a temperature difference, electric power can be produced. This arrangement is elegant because it avoids the complexity of mechanical generation systems. No spinning machinery is required. Few designs are better suited to a mission that must survive for decades with minimal maintenance and high reliability. Yet elegance does not mean abundance. RTGs are dependable, but they are not highly efficient in the ordinary sense. Much of the energy released as heat is not converted into electricity. Instead, it is lost as thermal radiation. Even so, for a spacecraft like Voyager, one efficiency in the everyday economic sense is less important than durability, predictability, and independence from sunlight. The RTG provides all three. It generates electricity continuously, day and night, regardless of where the spacecraft travels. It also supplies heat, which becomes an indirect resource of its own, because onboard systems must remain within workable temperature ranges. In earlier years, when electrical output is higher, the spacecraft can support a broader set of functions with less severe compromise. Over time, however, the decay of the radioactive fuel reduces the thermal power available. And because the thermoelectric conversion process depends on temperature difference, the electrical output falls as well. This decline is expected. It is built into the physics of the fuel itself. Radioactive decay follows a statistical law described by half-life, the interval over which a given quantity of material tends to reduce its activity by half. That does not mean the generator loses half its usefulness all at once. It means the output decreases gradually and predictably over long spans. For mission planners, this predictability is both a gift and a burden. It allows them to forecast future power availability, but it also means there is no surprise recovery waiting ahead. The general direction is always downward. In Voyager, one's case, that decline becomes one of the defining facts of the late mission. Every year, there is a little less electricity available for instruments, heaters, computers, communication systems, and the basic housekeeping functions needed to keep the spacecraft operational. This forces decisions that are not merely technical, but strategic. What should remain powered? What can be turned off? Which systems are indispensable? And which scientific capabilities can no longer be justified when measured against the need to preserve communication and control? The RTG therefore shapes not just the spacecraft's energy budget, but the mission's philosophy of survival. Another subtle aspect of RTG operation is that the power source ages in more than one way. The radioactive fuel loses output according to nuclear decay, but the thermoelectric elements and other parts of the system can also degrade with time. Materials exposed to long-duration heat gradients, radiation, and deep space conditions do not remain ideal forever. This means the decline in electrical power is influenced not only by the fuel's changing heat production, but by the performance of the conversion system itself. The result is a long downward curve, one studied carefully by engineers who must plan years ahead with no possibility of replacing the source. That planning involves more than counting watts. Power on board a spacecraft is tied to voltage stability, thermal conditions, load balancing, and operational scheduling. Some systems may demand power continuously. Others can be cycled or turned off permanently. Some heaters protect equipment from cold, but if power is scarce, even a heater can become a luxury. The RTG's diminishing output thus ripples through every part of mission management. It determines which instruments remain alive and which must fall silent. It affects how warmly the spacecraft can keep itself. It influences the margin available for anomalies, because a mission with little spare power has less flexibility when something unexpected occurs. And yet, there is a deep calm in the way the RTG supports Voyager 1. Unlike a battery draining toward an abrupt endpoint, it fades with a kind of measured honesty. It offers less each year, but it does so in a way that can be tracked, anticipated, and worked with. That gradual loss has allowed NASA engineers to adapt, incrementally preserving mission life far beyond what many would have imagined. The power source does not perform miracles. It provides a slowly shrinking foundation on which careful engineering can still build. There is also something fitting about the nature of this energy. Voyager 1 is a machine traveling in profound darkness, yet within it, a quiet internal warmth persists, generated by atomic change. That warmth becomes electricity. That electricity becomes telemetry, attitude control, scientific measurement, and the radio signal returning to Earth. In this chain, the deep laws of nuclear physics become part of a human story of persistence. The spacecraft remains connected because unstable nuclei continue their slow transformation, because engineered materials continue to turn temperature difference into current, and because mission teams continue to spend that current with extraordinary care. Voyager 1's power is not dramatic, not renewable in the ordinary sense, and not sufficient for comfort. It is finite, declining, and precious. But across nearly half a century, it has been enough to carry a machine beyond the heliosphere and keep it speaking from interstellar space. That is the quiet achievement of the RTG, not endless life, but a long, graceful diminishing that still sustains discovery. As the electrical output of Voyager 1 slowly declines, survival depends less on having enough power for everything, and more on deciding what can no longer be kept alive. This is one of the quietest and most difficult dimensions of the mission. The spacecraft does not face a single dramatic moment when all systems fail together. Instead, it faces a long sequence of choices imposed by a shrinking power budget. Each choice asks what is essential, what is valuable, what is still scientifically worthwhile, and what can be sacrificed so that the deeper purpose of the mission continues a little longer. In this late phase, engineering becomes an art of subtraction. The goal is no longer to operate a fully capable spacecraft in the broad sense imagined near launch. The goal is to preserve a narrow core of function communication with Earth-stable orientation, sufficient onboard computing, and as much scientifically meaningful measurement as the remaining power can support. Everything else is judged against those priorities. This process reveals an important truth about long-duration space missions. Endurance is not only a matter of robust hardware, it is also a matter of disciplined decision-making over time. Voyager 1 has survived in part because engineers have been willing to let parts of the mission go in order to save the mission as a whole. Every watt matters because each watt can be spent only once. The spacecraft's power is distributed among multiple needs. The radio system must transmit. The computers must remain active enough to process commands and manage spacecraft functions. The attitude control system must continue to keep the antenna pointed toward Earth with extraordinary precision. Scientific instruments, if they are to return useful data, must remain powered and thermally supported. Heaters may be needed to keep some components above minimum operating temperatures. Even the lines and electronics that distribute power have their own constraints. A reduction in available electricity is therefore not a simple reduction in comfort. It is a tightening of the entire life support structure of the spacecraft. The question becomes how to narrow that structure without breaking it. Some systems are clearly non-negotiable. If the spacecraft cannot point its antenna, communication may be lost. If communication is lost, the mission ceases to be operational no matter how many instruments remain nominally powered. If core computing fails, commands may not be interpreted correctly, and engineering telemetry may not return in useful form. These foundational functions are protected as long as possible. Around them lies a zone of harder decisions involving scientific instruments and support components, whose value must be weighed against the cost of keeping them alive. Not all instruments consume the same power. Not all remain equally useful in the environment Voyager 1 now inhabits. Some were built for conditions encountered earlier in the mission, during planetary flybys, or within regions where other data sources could complement them differently. In interstellar space, the scientific priorities change. Instruments capable of studying cosmic rays, particles, fields, and the local plasma environment may offer unique ongoing value. Others may become less central or less practical to maintain. Power management thus becomes linked to scientific triage. The mission is not abandoning science. It is refining science toward what only Voyager 1 can still do. The order in which systems are turned off matters too. A heater might not appear scientific in itself, yet turning it off can affect an instrument or subsystem in indirect ways. A component once assumed to require active heating may continue operating even at colder temperatures than originally expected. But this cannot be taken for granted without analysis and risk. Over the years, mission teams have learned that some hardware can tolerate colder conditions better than conservative early assumptions suggested. That discovery can extend life, but it also brings uncertainty. Operating beyond nominal thermal limits is not the same as safe operation in the ordinary sense. It is a calculated wager based on data history and the lack of better alternatives. In this late mission, necessity encourages a deeper understanding of the spacecraft's true margins. Some limits are absolute. Others turn out to be more flexible than expected. Engineers must distinguish between them with great care because a wrong judgment can end a system permanently. There is also the matter of sequence over time. Because the RTG output declines gradually, power-saving actions are often staged. One system may be turned off now to buy time for several more months or years of broader survival. Later, another cut may be required. This creates a mission timeline shaped not by expansion but by controlled contraction. It is almost biological in feel, though the spacecraft is not alive. Non-essential functions are shed first. Support becomes concentrated on the remaining core. The machine grows simpler as it grows older. Yet within that simplification, its meaning may become sharper. Voyager 1 in interstellar space does not need to be many things. It needs to be one extraordinary thing, a functioning probe returning rare measurements from a region no other active mission samples in the same way. The emotional weight of these decisions should not be overstated, but neither should it be ignored. Engineers working on Voyager 1 are not merely managing hardware in an abstract sense. They are custodians of one of the most significant exploratory machines ever built. Turning off an instrument is not a theatrical tragedy, but it can still feel like the closing of a long chapter. Many of these systems have histories stretching back decades through Jupiter-Saturn, the outer heliosphere, and into the interstellar medium. To let one go is to accept that the spacecraft's future can only be purchased by narrowing its present. Yet this narrowing is not defeat. It is the method by which continuity is preserved. A mission that insists on keeping every capability may end sooner than one that learns how to live with less. This is the central logic of power management aboard Voyager 1. Survival depends on reducing ambition without surrendering purpose. NASA's role in this process is both technical and interpretive. Teams must analyze power trends, thermal responses, instrument performance, command risks, and scientific return. They must ask not only what the spacecraft can still do, but what it should still do. The answer changes with time. A decision sensible 5 years ago may no longer be sensible now. The spacecraft ages. The environment remains harsh. Communication margins fluctuate. New anomalies can appear. Power management is therefore never finished. It is an ongoing practice of reassessment under constraint. In that practice, the mission's final years are not passive decline. They are active stewardship. Voyager 1 continues because people on Earth keep choosing with patience and rigor how to spend the last diminishing gifts of its radioactive power source. Some systems go dark so that others may keep working. Some possibilities are surrendered so that contact itself may survive. The result is a spacecraft increasingly reduced to essentials still alive, not by abundance, but but by discipline. In the deep cold beyond the heliosphere, Voyager 1 carries fewer active functions than before, yet each one that remains has been preserved intentionally. The mission endures because it has learned how to let go one careful decision at a time. Age in space is not simply the passage of years. It is the slow accumulation of stress across systems that can never be physically touched again. For Voyager, one age means electronics that have operated far longer than originally expected, materials that have endured repeated thermal cycles and prolonged exposure to radiation propulsion components that have fired again and again across decades, and structures that must remain aligned in an environment offering no maintenance and no direct inspection. Nothing aboard the spacecraft is exempt from time. Even when a system continues to function, it does so under the condition of having grown older in deep space. This does not always show itself through dramatic failure. More often, it appears as narrowing margin, as reduced certainty, as an increasing sensitivity to small changes in temperature, voltage, or performance. The spacecraft survives, not because time has ignored it, but because its original design combined with careful operations has allowed it to age more slowly than many would have imagined. Still, age is present everywhere in the mission's late phase. It shapes what engineers expect, what they fear, and what they try to preserve. One important part of this aging comes from the thermal environment. Voyager 1 carries some internal warmth from its power source and electronics, but that warmth has always had to be managed carefully. In the outer solar system and beyond, solar heating becomes weak, while radiative heat loss into space remains constant. The spacecraft exists in an ongoing balance between producing heat internally and losing it to the dark surroundings. As power declines, less waste, heat is available, and the temperature of some components can drift downward. Cold is not automatically fatal, but materials and devices have operating ranges for good reason. Lubricants, seals, circuits, sensors, and wiring can all behave differently at low temperatures. Some systems may continue below their nominal limits, while others may become unreliable or fail outright. Engineers therefore watch temperatures not as abstract numbers, but as indicators of how close particular components may be to trouble. Turning off a heater may save power, yet it can also expose a part of the spacecraft to conditions that were once avoided by design. In a young spacecraft, there may be generous thermal margin. In an old spacecraft, those margins become harder to assume. Age also affects the attitude control system, the collection of sensors, logic, and thrusters that keeps Voyager 1 properly oriented. Orientation is not optional. The high-gain antenna must remain pointed toward Earth within a very small angular tolerance if the radio link is to continue, and certain instruments must also maintain suitable orientation for their measurements. This requires occasional thruster firings to correct drift and preserve alignment. Over many decades, thruster use becomes a long record of accumulated wear. Valves open and close, propellant flows. Tiny impulses alter the spacecraft's motion. Each act is small, but together they form part of the physical history of the mission. A thruster system can endure extraordinary lengths of service, yet no engineer assumes such endurance without caution. Deposits can build. Performance can shift. Components can age under conditions impossible to reproduce exactly on Earth. Because attitude control is fundamental to communication itself, any sign of strain in this system receives serious attention. The challenge is heightened by distance. When a problem appears, it cannot be diagnosed by inspection. It must be inferred from behavior, from telemetry, from response patterns from the indirect language of engineering evidence. Electronics present another layer of vulnerability. Voyager, one's onboard computers and supporting circuits, belong to an earlier technological generation, one that in some ways favors robustness through simplicity. Yet age still matters. Electronic parts can drift, connections can weaken, memory systems can experience corruption. Radiation effects can alter behavior temporarily or permanently. Even when shielding and conservative design reduce these risks, decades of exposure create the possibility of anomalies that become more likely simply because the mission has lasted so long. And because the spacecraft operates with limited redundancy in some areas and limited flexibility in all areas, an anomaly that might be inconvenient in a newer or more richly resourced system can become mission-threatening here. Engineers must therefore think not just about what is broken, but about what remains barely healthy, what may fail next, and how much latitude the spacecraft still possesses. This atmosphere of narrowing confidence is one of the defining features of an aging machine in deep space. Materials themselves carry time differently in such an environment. Metals expand and contract with thermal change, though in smaller ways than everyday experience might suggest. Insulation ages. Surface properties can alter. Tiny mechanical tolerances that once seemed generous may become more consequential when combined with declining heat and power. None of this guarantees collapse. It only means that a spacecraft surviving into advanced age becomes less like a fresh machine operating within design expectations, and more like a long-standing structure supported by accumulated knowledge of its peculiarities. Operators learn its habits. They learn which readings fluctuate harmlessly, which trends deserve concern, and which assumptions from early mission phases no longer hold. This learned understanding becomes as important as the hardware itself. The spacecraft under strain is therefore both a physical reality and an interpretive one. Its condition exists partly in the machine and partly in the minds that continue to monitor it. There is also the strain created by communication delay. Any aging spacecraft near Earth might permit quick testing or immediate operational response. Voyager. One offers no such luxury. A command takes many hours to arrive. A reply takes many more hours to return. Every experiment, every adjustment, every diagnostic sequence unfolds slowly with long intervals between intention and knowledge. This means that uncertainty lasts longer. A suspected problem cannot be probed rapidly through trial and correction. Each step must be chosen carefully because feedback is expensive in time. Age, when combined with delay, becomes more than hardware degradation. It becomes a slower form of reasoning. The spacecraft lives on the far side of patience. And yet, strain does not mean helplessness. Voyager 1 continues to function precisely because its strain is managed rather than denied. Engineers conserve power, refine procedures, repurpose surviving capability, and accept that late life in deep space will always involve compromise. Some systems are colder than originally preferred. Some resources are tighter than originally planned. Some anomalies are handled not by restoring youthful condition, but by finding a workable path through old age. This is perhaps the most remarkable part of Voyager 1's endurance. It does not persist as a perfectly preserved machine. It persists as an aging machine with all the fragility that implies and still remains scientifically useful. Its survival is not static. It is negotiated continuously against cold distance, fading power, and the cumulative wear of time. In the darkness beyond the sun's dominant reach, Voyager 1 carries that strain quietly. It does not announce its age in any human way. It reveals it through telemetry, through operational constraints, through the growing delicacy with which each remaining capability must be treated. The spacecraft endures, but endurance here means something exact. It means continuing under pressure, continuing with less margin, continuing while old. Failures on Voyager 1 do not unfold in the manner people usually associate with malfunction. There is no visible smoke, no audible alarm, no technicians standing nearby to watch a warning light turn red. A problem emerges instead as an irregularity inside a stream of telemetry, a pattern that no longer matches expectation, a value that stops making sense, a signal that remains present while its contents become confused. Because the spacecraft is so far away, every failure arrives as delayed evidence. Engineers on Earth do not witness the event itself. They encounter its aftermath carried back by radio over many hours. This creates a special kind of uncertainty. Something has happened, but what happened must be inferred indirectly, and the clues may be incomplete. In that sense, failures on Voyager 1 belong not only to hardware, but to interpretation. A spacecraft at great distance becomes legible through traces, and when those traces change unexpectedly, diagnosis becomes a slow and careful act of reasoning. This is especially true for computer and communication problems, which can affect the very channel through which diagnosis must occur. Voyager 1 depends on onboard computers to manage different aspects of operation, including command handling, data formatting, attitude, control support, and the packaging of telemetry for transmission to Earth. These systems are limited by modern standards, but they are central to the mission's ability to remain coherent. A malfunction in one of them does not simply reduce convenience. It can alter how the spacecraft describes itself. If engineering data becomes garbled, contradictory, or stuck in an impossible pattern, then the mission team loses part of the map needed to understand the spacecraft's condition. A failure can therefore damage both the machine and the means of knowing the machine. This is one reason such events are so serious. They reach beyond the failed component and into the process of recovery itself. Some failures may appear suddenly, but many become visible first as anomalies that resist simple explanation. Telemetry may continue to arrive, yet the values may no longer correspond to any expected spacecraft state. A subsystem may seem to be both operating and not operating, depending on how the data is interpreted. A memory area may hold corrupted information. A command may be received but not produce the expected response. A transmitter may remain active while the data stream it carries loses internal coherence. In these moments, engineers must distinguish between several possibilities. The problem might lie in the spacecraft's sensing and reporting rather than in its core function. The spacecraft might be healthy enough to operate yet unable to describe its own health correctly. Or the fault might be deeper, affecting command execution, data storage, or internal control paths. These distinctions matter because a wrong diagnosis can lead to commands that worsen the situation instead of helping. Delay intensifies everything. A command sent today may not reach Voyager 1 for well over 20 hours. The spacecraft's response may not return until well over 20 hours after that. Even a simple test can therefore take nearly 2 days between question and answer, and a complicated investigation may stretch across weeks or months. This slowness changes the psychology of failure analysis. On Earth, engineers often isolate a fault by rapid iteration, trying one diagnostic step and then quickly adjusting based on the result. With Voyager 1, that style is impossible. Each step must be thought through in advance, not because caution is a virtue in the abstract, but because feedback, is so costly in time. Every command sequence becomes a wager on the quality of one's understanding. This makes deep space troubleshooting a discipline of delayed logic. The spacecraft must be treated almost like a historical source, revealing its condition through fragments that arrive from the past. Computer failures are particularly challenging because software and memory are forms of organized state. They determine how raw hardware behaves, how data is interpreted, and how instructions are carried out. If a region of memory becomes corrupted, the spacecraft may begin sending telemetry that no longer maps correctly to real conditions. If a processing path is disrupted, engineering data may be malformed, even while the radio carrier itself remains stable. A machine can thus appear nonsensical, not because it has entirely failed, but because the structure that gives meaning to its output has been disturbed. Restoring order may require identifying alternative memory locations, rewriting stored instructions, rerouting data paths, or using older and less preferred subsystems in creative ways. None of these actions is trivial when the machine is billions of miles away and built with technology from the 1970s. Knowledge of legacy architecture becomes crucial. Documentation matters. So does the experience of engineers who understand not only how the spacecraft was meant to behave, but how it has actually behaved over decades of aging workarounds and accumulated operational decisions. Communication failures bring another kind of complexity. Because the link itself is fragile, any loss of intelligibility raises the question of whether the problem lies in the spacecraft's transmitter, the formatting of its data, the pointing of its antenna, the receiving systems on Earth, or some interaction among these. A weak or drifting signal can mimic one class of fault while masking another. Engineers must therefore separate the existence of the radio carrier from the intelligibility of the information riding on it. Hearing something is not the same as understanding it. In some cases, the carrier may be present and trackable, confirming that the spacecraft still points roughly correctly and still transmits power while the telemetry remains unusable. That combination can be encouraging because it suggests the machine is not wholly lost, yet it also reveals how partial survival can complicate recovery. The spacecraft may be alive enough to speak, but not clear enough to explain what is wrong. Failures in deep time also accumulate a historical dimension. Voyager 1 is not a new system operating under ideal conditions. It is an old machine with previous anomalies, previous repairs, previous reconfigurations, and a shrinking power budget. Every new problem arrives within that larger context. An instrument already turned off for power reasons will not return as a source of diagnostic help. A heater already disabled may influence the behavior of nearby electronics. Old assumptions may need revision because the spacecraft now operates colder, leaner, and farther beyond its original mission design than anyone first intended. Diagnosis therefore becomes an exercise in layered memory. Engineers are not simply reading present telemetry. They are reading the present against decades of spacecraft history. What makes Voyager 1 remarkable is not the absence of failure, but the fact that failure does not automatically end the mission. Problems emerge, sometimes severe ones, and yet the spacecraft remains recoverable because enough parts of the system still function for reasoning to continue. There is still a signal. There is still command capability. There is still some space in which to test, interpret, and adapt. This does not make every failure solvable. It means only that the line between trouble and silence is not immediate. In that narrow interval, human patience and machine resilience meet. A computer fault or telemetry anomaly becomes not only a technical challenge, but a demonstration of how far sustained attention can reach. Across billions of miles delayed by the finite speed of light, a flawed and aging spacecraft continues to yield clues. Engineers study those clues and slowly reconstruct what can no longer be directly seen. In that reconstruction, failure becomes a kind of distant weather, difficult to predict, impossible to touch, yet still readable enough that action remains possible. To repair Voyager, one is to act on a machine that cannot be seen directly, cannot be touched, and cannot answer quickly. Every attempt at correction must cross a gulf of time as well as distance. A command leaves Earth, travels outward for more than 20 hours, reaches the spacecraft, is interpreted by aging electronics, and only then begins to produce a result that may not be known on Earth until another long interval has passed. In ordinary engineering, repair is often associated with proximity. A broken system is inspected, tested, adjusted, and tested again in relatively rapid sequence. With Voyager 1, none of those rhythms apply. Repair becomes an exercise in remote logic, built from patience, memory inference, and extraordinary restraint. The mission team must form a picture of a hidden machine, using only the signals that machine still manages to return. Then, based on that picture, they must decide what to change without any guarantee that the next reply will be easy to interpret. This transforms repair into one of the most disciplined forms of problem-solving in modern engineering. It begins with diagnosis, but diagnosis itself is inseparable from communication. A spacecraft billions of miles away does not present a fault in the familiar way. It presents clues. Telemetry values may become inconsistent. A data stream may remain present while its contents lose coherence. A command may appear to reach the spacecraft while the expected response never arrives. From these fragments, engineers build hypotheses. They ask whether the problem is likely rooted in memory data, formatting, sensor reading, attitude control, thermal state, or a path through onboard computers that no longer behaves as expected. The answer is rarely obvious. Multiple possible failures can produce similar outward signs. A value that looks impossible may reflect corrupted telemetry rather than a damaged subsystem. A silent response may suggest command failure transmitter weakness or a problem with how the spacecraft packages outgoing data. The first task of remote repair is therefore not fixing, but narrowing uncertainty. Engineers do this by sending carefully chosen test commands, each designed to reveal something specific while minimizing risk. This is where distance changes the nature of reasoning. On Earth, a test can be treated almost casually because results return quickly, and another adjustment can follow within minutes. With Voyager 1, a test command is expensive in time. It must be worthwhile. It must be structured so that the possible outcomes can meaningfully distinguish one hypothesis from another. A poor test wastes not only time but opportunity. A risky test can endanger a fragile system whose remaining margins are already narrow. The engineers therefore proceed slowly, building a ladder of logic from the most conservative actions upward. They begin by asking what the spacecraft can still be trusted to do. Can it maintain pointing? Can it receive commands consistently? Can it return any valid engineering information? Can an alternate path through the onboard computers be used to verify behavior? These questions define the space in which repair is possible. Once that space is understood, actual corrective action may involve rewriting data into different memory locations, commanding the spacecraft to use alternate procedures, bypassing damaged sections of code, or reconfiguring the flow of information so that usable telemetry can once again reach Earth. Such actions sound abstract, but their abstraction is part of the challenge. The spacecraft is not repaired by replacing a part. It is repaired by altering patterns of behavior inside a machine that has no spare human hands nearby. The engineers work with logic rather than tools. A memory region that seems compromised may be avoided. A function once handled in one way may be shifted to another. A sequence that no longer works reliably may be broken into smaller or safer parts. Repair in this context often means adaptation rather than restoration. The goal is not always to return Voyager 1 to an earlier ideal condition. Often that is impossible. The goal is to recover enough order and capability that the mission can continue. This distinction matters because it reflects the true nature of old age in a spacecraft. The mission is not searching for youth. It is searching for survivable function. There is also a remarkable conservatism in how remote repairs are planned. Commands are reviewed carefully because once transmitted, they cannot be recalled. They move outward at the speed of light and will either be executed or not, depending on spacecraft state and correctness of the sequence. This gives each command a kind of weight, uncommon in ordinary computing. A mistaken command can consume precious time, worsen confusion, or in the worst case, threaten the remaining health of essential systems. Teams therefore cross-check procedures. Consider fault protection behavior. Think about unexpected interactions and sometimes choose slower but safer approaches over more ambitious ones. The finite speed of light encourages humility. Even success unfolds slowly. Suppose engineers identify a likely software or memory-related issue and send a corrective command. The command travels outward for many hours. The spacecraft receives it and attempts to act. Then the spacecraft's response travels back for many more hours. By the time Earth learns whether the step worked, nearly 2 days may have passed. If the result is partial, another command sequence must be devised, sent, and awaited. A complex repair can therefore stretch across long periods, not because the team lacks urgency, but because physics imposes a measured pace on every interaction. This means morale and discipline matter as much as technical knowledge. Engineers must remain methodical under slow feedback, able to hold complex states of reasoning across days and weeks. They must resist the urge to overcommand, to send too many changes at once, or to interpret ambiguous evidence too quickly. The craft of repair lies partly in knowing how little to change at one time. Voyager 1's remote repairs are also remarkable because they depend on continuity of knowledge across generations. The spacecraft was designed and launched in the 1970s. Many of the people currently helping sustain it belong to later eras of engineering culture with different tools, different training environments, and different assumptions shaped by modern systems. Yet they must still understand the old architecture on its own terms. This requires documentation, institutional memory, archival knowledge, and a willingness to think like the engineers who first built the mission. In some cases, it also requires new creativity applied to old hardware, finding ways to use surviving capabilities that may not have been part of the most ordinary operational path. The repair becomes a collaboration across time. Present-day analysts reasoning with the intentions of designers from half a century earlier, all mediated through a spacecraft still obeying the laws and limitations of its original construction. What emerges from this process is not a dramatic image of rescue, but something quieter and in many ways more impressive. A distant machine falters. Earth notices through faint, delayed clues. Human minds assemble those clues into a model of hidden failure. Commands are crafted, checked, and sent into the dark. Days later, A slightly more coherent reply arrives, then another. Gradually, order returns. The spacecraft does not become young again. It becomes understandable again, and therefore useful again. That is the true nature of repairing Voyager 1 from billions of miles away. It is not force overcoming distance. It is distance being met with patience, logic, and disciplined care. Across interstellar space, remote repair becomes a form of sustained reasoning, so precise that even an aging spacecraft in the dark can still be guided back toward clarity. Long before Voyager, one becomes an emissary from interstellar space. It is a spacecraft of the planetary frontier. Its present distance and endurance can make it seem as though it belongs only to the dark beyond the heliosphere. Yet the mission's identity is rooted just as deeply in the worlds it once passed. Jupiter and Saturn are not merely earlier chapters in a long journey. They are the places where Voyager 1 first reveals the extraordinary power of close observation from a moving machine. They are also the reason the spacecraft acquires the velocity and trajectory that later carry it outward toward the edge of the Sun's influence. To understand Voyager, one only as a distant signal source, is therefore to miss half its significance. The craft, now crossing interstellar space, is the same one that once approached giant planets and transformed scientific understanding of those systems. Its deep future grows directly from that planetary past. The encounter with Jupiter brings the first great expansion of the mission's scale. Before Voyager 1 arrives, Jupiter is already known as the largest planet in the solar system, a world of bands, storms, and many moons. But much of that knowledge remains telescopic and incomplete. From Earth, even the best observations are limited by distance, atmosphere, and viewing geometry. Voyager 1 changes this by entering the Jovian system and observing it at close range, not with a single glance, but with a sustained sequence of measurements and images as it speeds through. What it finds is not a simplified version of what had been expected. It finds greater dynamism, greater detail, and greater complexity. Jupiter's cloud tops show a turbulent atmosphere organized into belts and zones, with storms and vortices moving through layered circulation. The great red spot, already famous before the mission, appears not as a static mark, but as part of a living weather system on a world driven by deep internal heat as well as solar input. The planet's atmosphere reveals motion on a scale beyond anything on Earth, yet also a structure delicate enough to show wave streaks and interactions between adjacent flows. Voyager 1's measurements help turn Jupiter from a distant object of observation into a physical system with texture, energy, and internal process. The magnetic environment around Jupiter proves equally striking. The planet possesses an enormous magnetosphere, a region in which charged particles are trapped and guided by magnetic fields. This environment is not incidental. It shapes radiation conditions, affects the space around the moons, and reveals Jupiter as a kind of miniature planetary system in itself, with interactions extending far beyond the visible cloud tops. Voyager 1's instruments encounter this magnetic domain, directly measuring particles and fields in ways impossible from Earth. The giant planet emerges not only as a globe of gas and weather, but as a center of energetic activity embedded in a large and structured space environment. Yet it is the moons that perhaps most dramatically alter scientific imagination. Among them, Io stands out with startling force. Instead of a quiet, cratered body marked only by ancient impacts, Io reveals active volcanism, a surface shaped by ongoing eruptions and internal heat. This discovery is one of the mission's most profound surprises. It shows that small worlds can remain geologically alive under the influence of tidal forces, the repeated flexing caused by gravitational interaction with Jupiter and neighboring moons. In Io, heat generated by orbital stress becomes visible as eruption and resurfacing. A moon once expected to be inert appears restless and changing. Europa, Ganymede, and Callisto also reveal new complexity. Their surfaces differ from one another in age, texture, and composition, suggesting distinct geological histories rather than simple repetition. Europa, in particular, presents a bright marked surface, hinting at processes that later missions and studies would consider in relation to subsurface water and ice dynamics. Voyager 1 does not answer all such questions, but it changes the terms in which they can be asked. The Jovian system is no longer a set of distant points circling a giant planet. It becomes a family of diverse worlds, each shaped by its own history and by its relationship to Jupiter. Saturn then offers a different kind of magnificence. If Jupiter is a system of overwhelming scale and energetic force, Saturn presents refinement, structure, and subtlety. The planet itself shows atmospheric patterns quieter in appearance than Jupiter's, but no less important scientifically. Its winds, banding, and seasonal character add to comparative understanding of giant planet atmospheres. But the most iconic feature the ring system becomes under Voyager 1's scrutiny, a realm far more intricate than telescopes had fully revealed. The rings are not simple flat bands. They are composed of countless particles arranged into divisions, strands, and structures shaped by gravity collisions and resonances with nearby moons. Voyager 1's observations help reveal the rings as a dynamic disk, a system in constant local interaction rather than a static ornament. This deepens planetary science far beyond the aesthetic wonder that Saturn had long inspired. Beauty and mechanism become inseparable. The encounter with Titan, Saturn's largest moon, also leaves a lasting mark. Titan's atmosphere is thick and hazy, obscuring the surface from ordinary visible view and announcing a moon more meteorological than many expected. Its dense envelope of nitrogen and complex chemistry makes it one of the most Earth-like worlds in atmospheric richness, even though its temperatures and conditions are profoundly alien. Voyager 1's trajectory is shaped in part by the decision to perform a close Titan flyby, a choice with major consequences. Scientifically, Titan is compelling enough to justify the path. Dynamically, that path bends Voyager 1 out of the plane that would have allowed visits to Uranus and Neptune. Voyager 2, not Voyager 1, goes on to those later planetary encounters. Voyager 1 instead takes the route that eventually carries it toward the heliosphere's outer limits and beyond. This is one of the mission's quiet turning points. A decision made for planetary science helps define the future in which the spacecraft becomes the first human-made object to enter interstellar space. The planetary past and the interstellar future are therefore not separate missions joined by accident. They are one continuous trajectory shaped by gravity and choice. Looking back from the present, Jupiter and Saturn seem almost luminous with historical closeness. They are worlds. Voyager 1 once passed in hours, and days worlds whose systems it transformed through direct encounter, and worlds now unimaginably far behind it. Yet their importance has not faded. The discoveries made there remain part of the spacecraft's identity and part of modern planetary science. The probe, now known for its faint signal from the interstellar medium, is also the probe that showed active volcanism on Io, deepened understanding of giant planet magnetospheres, revealed ring structure at Saturn, and expanded the scientific meaning of outer solar system moons. This matters Because Voyager 1's endurance is not empty persistence. It continues after a life already full of discovery. Its signal from the dark is powerful not only because it still exists, but because of everything that signal represents. It comes from a spacecraft that has already changed human knowledge of the giant planets and then kept going. Jupiter and Saturn are behind it now, but they remain carried within the mission as evidence of what one long journey has already made visible. Beyond the orbits of the outer planets, the solar system does not simply end in a clean and visible line. Its outermost region is shaped instead by a long interaction between the Sun and the galaxy around it. The Sun continuously releases the solar wind, a flow of charged particles moving outward through space, carrying with it embedded magnetic fields and creating a vast bubble of influence around the solar system. This bubble is called the heliosphere. It is not a solid shell, nor is it perfectly symmetrical. It is a dynamic region formed by pressure-motion plasma and magnetic structure, changing in response to solar activity and to the conditions of the interstellar medium outside it. Voyager 1, after passing the major planets and continuing outward for decades, approaches this distant frontier, not with eyes in the ordinary sense, but with instruments capable of reading particles, fields, and the subtle signatures of transition. The edge of the heliosphere is therefore not seen as a horizon. It is inferred from changing measurements, from shifts in what dominates the local environment, and from evidence that the Sun's outward wind no longer controls space in quite the same way. To understand this boundary, it helps to begin with the solar wind itself. The Sun is not only a source of light and gravity. It is also a source of plasma, a state of matter in which electrons and atomic nuclei move freely rather than remaining bound into neutral atoms. This plasma streams outward from the Sun in all directions, carrying energy and magnetic field into the solar system. Near Earth, the solar wind already shapes magnetic storms, auroras, and many aspects of space weather. Far beyond Earth, its influence continues, though not unchanged. As the wind expands, it becomes more diffuse. It still moves outward, but it does so into an environment that is not empty. The Sun travels through the galaxy, and the surrounding interstellar medium contains its own sparse gas plasma and magnetic field. At great distance from the Sun, the pressure of the outward solar wind must eventually meet resistance from that external medium. The heliosphere exists because of this meeting. It is the region in which the Sun's outflow has carved out a domain of influence, even while being shaped and constrained by what lies beyond. The approach to the edge of this domain is not simple. One important region is the termination shock, where the solar wind, still moving outward but no longer able to remain supersonic, relative to local conditions, slows abruptly and becomes hotter and more compressed. This does not mean a shock in the everyday sense of collision between solid objects. It is a plasma phenomenon, a transition in flow behavior as the solar wind encounters the growing opposition of the surrounding medium. Beyond that lies the heliosheath, a broad and complex region where the slowed solar wind continues outward in a more turbulent and compressed state. The heliosheath is not yet interstellar space, but it is no longer the relatively free-streaming solar wind of the inner heliosphere. It is a boundary zone, a place where the Sun's influence remains present, yet altered, pushed and increasingly negotiated. Voyager 1 travels through this region for years, and the passage reveals how gradual and structured the outer frontier truly is. The heliopause then marks the boundary between the solar wind-dominated plasma and the interstellar plasma outside. It is often spoken of as the edge of the heliosphere, and in a broad sense that is correct, but the term can sound sharper than the reality experienced by instruments. The heliopause is not a painted line in space. It is a contact boundary between different plasma regimes, a location where outward flowing solar material gives way to the medium of the galaxy. Crossing it does not produce a sudden visual transformation. Instead, it is recognized through changes in particle populations, field behavior, and plasma characteristics. The challenge is that each measurement must be interpreted carefully. Space is full of gradients, fluctuations, and temporary events. A single reading is rarely enough to establish that a major boundary has been crossed. Scientists look instead for persistent changes that together tell a coherent story. Voyager 1's approach to this frontier is scientifically rare because no other active spacecraft has sampled the same boundary in the same way at such distance. The spacecraft becomes a moving sensor inside a transition humanity had previously understood largely through theory and indirect evidence. One important clue comes from energetic particles. Inside the heliosphere, many particles are accelerated or modulated by solar processes. As Voyager 1 nears the heliopause, the populations of these particles change, while particles associated more strongly with the interstellar medium become increasingly prominent. This changing balance provides one sign that the spacecraft is nearing or entering a new regime. Magnetic field measurements also matter, though they complicate the story. Scientists might expect a boundary between solar and interstellar domains to show a dramatic change in magnetic direction. But nature is not obliged to produce simple textbook signatures. The field behavior near the heliopause can be subtly shaped by how solar and interstellar fields interact locally. This is one reason the interpretation of the crossing requires multiple lines of evidence rather than reliance on a single expected marker. Plasma behavior offers another critical line of understanding. Plasma density beyond the heliopause differs from that inside the heliosphere, and certain instrument readings, including responses to plasma oscillations, can help estimate the density of the surrounding medium. Higher densities, consistent with interstellar expectations, provide strong support for the conclusion that Voyager 1 has crossed the heliopause. Yet even this understanding emerges gradually assembled from the relation between measurements, rather than announced by one dramatic instrument event. The edge of the heliosphere therefore teaches a broader lesson about science at great distance. Boundaries in nature are often not the neat borders suggested by language. They are regions of transition places where one governing balance gives way to another through structure variation and incomplete symmetry. The sun's influence does not simply stop. It weakens, compresses, and meets the galaxy in a complicated negotiation. Voyager 1's data allows that negotiation to be studied directly. The spacecraft does not merely move outward through space. It moves outward through definitions, forcing scientists to ask what it means for a star's environment to end and for interstellar space to begin. At the same time, the heliosphere remains part of a larger living system. Solar activity changes over cycles, and those changes propagate outward over time. The outer boundary can shift in response. The heliosphere may expand or contract somewhat depending on solar conditions and the pressure of the surrounding medium. This means the frontier is not static. It breathes on long timescales shaped by forces both from the Sun and from the galaxy beyond. Voyager 1 reaches this edge not as a passive witness, but as an instrumented traveler arriving after a long planetary past and before an even longer interstellar future. In the outer darkness, where sunlight is weak and the major planets are far behind the spacecraft, encounters the true perimeter of the Sun's environmental domain. There, in changes of particles, plasma, and magnetic structure, the boundary becomes real. Not visible, not dramatic in the human sense, but real in data. The heliosphere's edge is the place where the solar system ceases to be only a family of orbiting worlds and reveals itself as a bubble in the galaxy, and Voyager 1 is the craft that carries human measurement to that distant threshold. When Voyager 1 is said to have entered interstellar space, the statement sounds simple, but the reality behind it is careful and technical. The phrase suggests a clean crossing from one obvious place into another, as though the spacecraft had passed a gate marked by a visible sign. In practice, the crossing is defined not by appearance, but by evidence. Scientists must decide what counts as leaving the heliosphere and what measurements are strong enough to support that conclusion. This matters because space does not organize itself for human convenience. The boundary between the Sun's domain and the local interstellar medium is real, but it reveals itself through changes in particles, plasma, and magnetic conditions, rather than through any dramatic visual transformation. Voyager 1 therefore reaches interstellar space not with spectacle, but with data. The crossing becomes one of the most significant scientific interpretations of the mission's later years, precisely because it requires multiple kinds of evidence to build a consistent picture of where the spacecraft now is and what kind of environment surrounds it. One of the clearest indicators comes from particle populations. Inside the heliosphere, the Sun influences the distribution and behavior of many energetic particles. Some originate from solar processes, and others from the broader galaxy are modulated by the solar wind and the magnetic structures it carries. As Voyager 1 approaches the outer boundary, this balance begins to shift. Particles associated with the heliosphere decline, while galactic cosmic rays, high-energy particles arriving from beyond the solar system, become more prominent. This change is not merely a curiosity. It reflects the weakening hold of the Sun's plasma environment on the local particle population. When the spacecraft begins to register a sustained increase in galactic cosmic rays, together with a decline in particles more characteristic of the inner solar domain, scientists recognize that the surrounding conditions are changing in a fundamental way. The spacecraft is no longer simply deeper within the heliosphere. It is approaching or entering a region governed by a different balance of matter and energy. Yet, particle evidence alone does not settle the question completely. Boundaries in plasma physics can be complicated, and temporary effects may mimic aspects of transition. Researchers therefore look for other signals. Plasma density becomes one of the strongest among them. The interstellar medium, though still extraordinarily thin by terrestrial standards, has a different plasma density from the plasma within the outer heliosphere. If Voyager 1 can provide evidence that the surrounding plasma density has risen to values expected for the local interstellar environment, then the case for crossing becomes much stronger. Through analysis of plasma oscillations, essentially waves or vibrations in the plasma that can be linked to local conditions, scientists infer densities consistent with interstellar space rather than with the heliosheath. This matters greatly because plasma density is not just an abstract property. It tells scientists something direct about what kind of medium now surrounds the spacecraft. Higher density values matching interstellar expectations help anchor the interpretation in measurable local reality. Magnetic field behavior adds both support and complexity. At first glance, it might seem that the magnetic field direction should change sharply when Voyager 1 crosses the heliopause. If the heliosphere and the interstellar medium are different environments, then perhaps their magnetic signatures should be obviously distinct. But nature is subtler than that expectation. The measured field does not exhibit the dramatic directional shift some had once imagined as the clearest marker. Instead, the field remains more similar across the boundary than a simple picture might predict. This does not invalidate the crossing. It reveals that the local interaction between solar and interstellar magnetic fields is more nuanced. The boundary can be crossed even if the field geometry changes gently or remains locally aligned in ways not anticipated by the most straightforward models. This is one reason the conclusion depends on synthesis. Scientists do not rely on a single signature. They compare particle changes, plasma density, magnetic conditions, and the persistence of these changes over time. Together, these lines of evidence indicate that Voyager 1 has moved beyond the heliopause into the local interstellar medium. The importance of this crossing extends beyond naming a location. It changes what the spacecraft represents scientifically. Before the crossing, Voyager 1 is a probe of the outer heliosphere and its boundary regions. After the crossing, it becomes a direct sampler of interstellar space, at least of the local environment through which the solar system itself moves. This does not mean the spacecraft is suddenly traveling between stars in the popular imaginative sense. It is still much closer to the Sun than to any other star. It remains gravitationally bound to the Sun. But the medium around it is now interstellar in the operational scientific sense. The Sun's wind no longer dominates the local plasma. Instead, Voyager 1 is immersed in the sparse material of the galaxy. That distinction is the heart of the crossing. It is not about destination. It is about environment. Another reason this threshold matters is that it tests theoretical understanding. For many years, the outer boundary of the heliosphere had been modeled using principles of plasma physics, magnetohydrodynamics, particle transport, and solar wind behavior. Voyager 1 provides direct measurements against which those ideas can be checked. Some expectations are confirmed. Others require refinement. The subtle magnetic signature, the structure of the transition, and the details of the local plasma all deepen scientific understanding of how a star interacts with the interstellar medium around it. In this way, the crossing is not just a symbolic achievement. It is a data-rich event that forces theories to become more precise. It reveals that the edge of the Sun's influence is neither mystical nor trivial. It is a physical boundary shaped by competing flows fields and pressures, and it can be studied through patient measurement. The event also carries a quiet historical weight. Voyager 1 is the first human-made object to enter interstellar space. That fact is often stated in celebratory terms, but the deeper meaning lies in what kind of first it is. It is not the first arrival of humans themselves, nor the first step toward another star in any practical travel sense. It is the first extension of direct human instrumentation into a region once known only through remote inference. A machine launched in the 1970s, built with limited computing power and designed initially for the outer planets, becomes the first craft to cross this threshold and remain in communication with Earth. The crossing therefore joins two forms of achievement. One is exploratory, the reaching of a new environment. The other is epistemic, the gaining of direct knowledge about that environment. Voyager 1 does not merely go farther. It changes what can be known firsthand. Even after the crossing, the meaning of interstellar space remains modest and exact. The local interstellar medium is not dense, not bright, and not filled with dramatic scenery. It is thin plasma magnetic structure, cosmic rays, traces of gas, and the larger galactic context within which the heliosphere floats. So yet, precisely because it is so difficult to sample directly, every measurement matters. The threshold is crossed not with fanfare, but with a sustained shift in the language of the data. Particle counts change. Plasma density reveals a new medium. The balance of local influence is transformed. Through those quiet signs, Voyager 1 passes from the Sun's outer frontier into the galaxy beyond, and the crossing becomes real, not because it can be seen, but because it can be measured. After crossing into interstellar space, Voyager 1 does not become merely symbolic. It continues to function as a scientific instrument, and that continuing function is one of the most remarkable aspects of the mission's late life. The spacecraft is old, its power is diminishing, and the range of active systems has narrowed over time. Yet it still measures conditions in a region that remains almost entirely inaccessible by any other direct means. This makes its surviving instruments unusually valuable. They are no longer studying planets' moons or ring systems. They are studying the local interstellar medium itself, the sparse environment through which the solar system moves as it circles the galaxy. In practical terms, this means Voyager 1 continues to report on energetic particles, cosmic rays, magnetic field structure, and plasma conditions, helping scientists understand not only what lies beyond the heliosphere, but also how the heliosphere interacts with that larger galactic setting. The mission at this stage is quiet, slow, and highly constrained. Yet the science remains real because the region is real, and because measurements from within it are rare. One of the central scientific contributions of Voyager 1 in this phase involves cosmic rays. These are high-energy particles, many of them protons or atomic nuclei moving through space at enormous speeds. Some originate from violent processes elsewhere in the galaxy, including shock waves associated with stellar explosions and other energetic astrophysical environments. Inside the heliosphere, the intensity and energy distribution of cosmic rays are influenced by the solar wind and the magnetic fields carried outward from the Sun. The heliosphere acts partly as a shield, modulating how many galactic cosmic rays penetrate into the inner solar system and how their spectra appear at different locations. Once Voyager 1 moves beyond the heliopause, it begins sampling cosmic rays in a region no longer dominated by that shielding effect. This is scientifically important because it provides a clearer view of the local galactic particle environment. The spacecraft helps reveal the background against which the heliosphere had been filtering and reshaping incoming cosmic radiation. In this sense, Voyager 1 is not simply measuring distant particles. It is helping define the difference between conditions inside and outside the Sun's plasma bubble. That comparison has consequences for heliophysics, for models of cosmic ray transport, and for broader understanding of how stellar systems interact with the galaxy around them. The magnetic field is another major area of continuing measurement. Space is not empty of structure merely because it lacks dense matter. Magnetic fields thread through plasma and help shape the movement of charged particles, the transfer of energy, and the boundaries between different space environments. Voyager 1's magnetic field data allows scientists to examine the local orientation and strength of the field in the interstellar medium near the heliosphere. This is valuable not only because the field itself matters, but because it helps interpret other observations. Particle motions depend strongly on magnetic geometry. Boundary structure at the heliopause depends partly on how solar and interstellar fields interact. Waves and disturbances in plasma can propagate differently depending on field conditions. By continuing to measure the field beyond the heliosphere, Voyager 1 provides a direct point of contact between theory and observation. The measurements do not reveal a simple or perfectly uniform medium. Instead, they suggest local structure variation and subtlety. Interstellar space near the Sun is sparse, but it is not featureless. It contains organization at scales that become visible only through patient and sustained instrumentation. Plasma remains equally important. In space, physics plasma is not a secondary detail. It is one of the dominant forms of ordinary matter in many cosmic environments. The local interstellar medium around Voyager 1 contains ionized material whose density wave behavior and interactions help define the nature of the region. Through observed plasma oscillations and related signatures, scientists can estimate local electron density and track how conditions vary over time. These measurements strengthen the conclusion that the spacecraft is in interstellar space and also help characterize that space more precisely. Density in this context is still astonishingly low by everyday standards, but low density is not the same as no density. Even a tenuous plasma can carry waves support magnetic interaction and shape the propagation of energetic particles. Voyager 1's data therefore fills in a portrait of the local interstellar medium as a physical environment with measurable properties, rather than as an abstract emptiness beyond the solar system. Another important dimension of the continuing science lies in time variation. Voyager 1 is not taking a single snapshot and then falling silent. It is measuring over extended periods, and that duration matters. The interstellar medium is not frozen. Disturbances from solar activity can propagate outward over long timescales and influence conditions near the heliopause and beyond. The boundary itself may shift or respond to changing solar pressure. Waves can travel through plasma. The cosmic ray environment can vary. Because Voyager 1 remains active year after year, it offers not only location, but continuity. Scientists can observe how the local interstellar environment behaves over time, rather than relying entirely on one crossing event. This is a subtle but powerful advantage. In many branches of science, repeated measurement is what turns isolated fact into dynamic understanding. Voyager 1 brings that possibility to a region where direct access is otherwise absent. The scientific value is heightened by the fact that the local interstellar medium sampled by Voyager 1 is the medium immediately surrounding the heliosphere. This makes the spacecraft's measurements relevant, not just to distant astrophysics, but to the solar system's own galactic context. The Sun is not isolated. It moves through the Milky Way carrying its planets within a heliosphere that responds to external pressure, magnetic orientation, and surrounding interstellar conditions. To understand the heliosphere fully, scientists must also understand what lies outside it. Voyager 1 helps provide that outside perspective. It informs models of how the Sun's bubble is shaped, how cosmic rays enter it, and how the outer boundary may behave under changing conditions. In this sense, the spacecraft remains part of solar science even after leaving the heliosphere, because the heliosphere cannot be understood without reference to the medium into which it is embedded. There is also a quiet methodological lesson in the continuing mission. Science in this domain is not made through dramatic imagery or immediate spectacle. It is made through patient accumulation of particle counts, field strengths, densities, wave signatures, and long-term trends. The data can seem austere compared with the visual richness of planetary flybys. Yet austerity is not poverty. It is another form of richness, one that reveals physical reality through measurement, where ordinary human intuition has little foothold. Voyager 1's instruments are therefore doing something rare. They are translating an invisible region into terms that theory can use and that observation can test. Each surviving instrument contributes to this translation as long as power and spacecraft health permit. The mission's scientific future is finite because the power source continues to decline and more systems will eventually have to be shut down. Yet while the instruments remain active, Voyager 1 continues to offer a direct report from the galaxy just beyond the Sun's reach. It measures cosmic rays less shaped by solar shielding magnetic fields belonging to the local interstellar environment and plasma properties that reveal the physical texture of that environment. These are not grand sights in the visual sense. They are precise signs of place. Through them, Voyager 1 still does what exploration at its most disciplined has always done. It turns a distant unknown into a measured reality, one faint transmission at a time. Voyager 1 endures in a form no one at the beginning of the mission could fully expect. It is no longer the young planetary explorer that rushes past Jupiter and Saturn, carrying a wide array of active possibilities. It is an aging spacecraft in the dark, reduced year by year to a smaller set of essential functions sustained by dwindling electrical power and by the continuing effort of engineers who know that every remaining capability must be treated with care. Yet this reduction has not diminished its meaning. In some ways, it has clarified it. The spacecraft has become a study in endurance itself, a long-lived human artifact whose value now lies not in abundant speed or spectacle, but in persistence. It continues because enough of its systems still work, because enough of its internal order can still be maintained, and because the relationship between the machine and Earth has not yet been broken. That relationship is perhaps the deepest source of the spacecraft's significance in its late years. Voyager 1 is distant beyond ordinary comparison, and still it remains in contact. This is not merely an engineering success. It is a sustained extension of human attention across a scale that resists ordinary thought. The mission's endurance begins with the spacecraft as an object. Built in the 1970s from hardware that now belongs to another technological age, Voyager 1 carries the physical assumptions of that era far beyond their original horizon. It is made of metal circuitry, insulation, propellant lines, sensors, memory, antenna structure, and thermoelectric power systems, all assembled for a mission that was never expected to remain scientifically active for nearly half a century. Most human artifacts are made for short use, easy replacement, or frequent maintenance. Voyager 1 belongs to a rarer class of object, one built to survive, where maintenance is impossible and replacement has no meaning. It carries within it a different philosophy of construction, one in which longevity, redundancy, and operational clarity matter more than novelty. That philosophy has allowed it to outlast many institutions, many technologies, and even many of the cultural assumptions present at its launch. It survives because it was built with discipline, and because that discipline has continued on Earth in the people who keep listening and responding. There is a tendency to describe such endurance in heroic language, yet the spacecraft itself is not heroic in any conscious sense. It does not strive. It does not decide. It follows physics, engineering logic, and the commands that still reach it after long hours of travel through space. Its endurance is therefore a collaboration between machine and stewardship. The machine provides the remaining capability. Human operators provide the judgment about how that capability is used. As power falls, instruments are turned off. As thermal margins narrow, assumptions are revised. As anomalies appear, repairs are attempted through logic and patience. The mission continues, Not because Voyager 1 is immortal, but because it is still just alive enough to reward careful management. This gives its endurance a quiet honesty. It is not the fantasy of endless survival. It is survival under visible constraint. Every year asks a little more of the shrinking power supply. Every year reduces flexibility. Every year moves the spacecraft farther into a region where no intervention except radio command is possible. And still within those limits, it remains operational. The phrase "still alive" acquires a very precise meaning in this context. It means the spacecraft can orient itself, receive commands, return telemetry support, a small number of scientific measurements, and maintain internal coherence despite age and cold. It does not mean fullness of function. It means enough function to remain meaningful. This distinction may be one of the mission's deepest lessons. In much of ordinary life, worth is associated with expansion, with doing more, with maintaining every capability. Voyager 1 demonstrates another form of worth. It demonstrates that continuity itself can be profound when continuity is unlikely. A machine need not remain complete to remain valuable. It need only preserve a narrow bridge between existence and knowledge. Voyager 1 still does that. From beyond the heliosphere, it continues to tell Earth something true about where it is and how that place behaves. That continuing truth is enough to justify the effort required to sustain the mission. There is also a broader cultural meaning to the spacecraft's endurance. Voyager 1 is often described as one of humanity's farthest emissaries, and the phrase is useful if treated carefully. The craft does not speak for humanity in any moral or political total sense. It is not a conscious representative. But it does carry outward a material consequence of human curiosity, engineering, and long-term planning. It represents the fact that a species confined to one small planet has learned how to build instruments that can cross the outer planets, leave the heliosphere, and continue reporting from the local interstellar medium. In this sense, Voyager 1 is not only a spacecraft, it is a durable record of what patient inquiry can produce. It shows that exploration need not end where direct human travel ends. Instruments can carry attention farther than bodies can go, and they can carry it with fidelity if the connection is preserved. This idea becomes especially powerful in the spacecraft's old age, because old age strips away distraction. What remains is the essential fact of connection. A weak signal arrives. It contains traces of a distant machine. Those traces can still be understood. The line has not yet gone silent. Eventually, of course, silence will come. The power source will continue to decline. More systems will be turned off. A final threshold will be crossed at which communication or control can no longer be maintained. Voyager 1 will then continue outward as a silent object, no longer part of an active mission, but still part of history, carrying its golden record and its physical presence into the long future of the galaxy. Yet the coming of that silence does not diminish the present achievement. It makes the present more precious. Every remaining transmission is an event made unlikely by distance time and aging hardware. Every bit returned is evidence that the chain still holds. The mission endures on borrowed margin, on dwindling watts, on careful choices, on delayed reasoning, and on the fact that an old spacecraft from 1977 has not yet exhausted its capacity to remain in relationship with its makers. That relationship is the quiet center of Voyager 1's impossible mission. It is beyond the outer planets, beyond the heliosphere, beyond the environment where the sun still governs the local plasma, and still it turns its antenna toward Earth. Still it sends. Still Earth listens. In that continuing exchange, the spacecraft becomes more than a machine and less than a myth. It becomes a precise and humble testament to endurance beyond expectation, a small constructed object carrying the long persistence of human attention into the dark between the stars. In the long quiet, after so many measurements, repairs, and distant returns, Voyager 1 continues outward with no change in intention, only the steady continuation of motion given long ago. Behind it lie the giant planets, the outer heliosphere, the crossing into interstellar space, and decades of patient listening from Earth. Around it lies a sparse medium of particles fields and darkness too thin for ordinary imagination, yet real enough to be measured by a small surviving set of instruments. Within it remains a diminishing source of warmth and electricity, still enough for a little order, still enough for a little speech. The spacecraft does not know the scale of its own journey. It does not know that it has become one of the most enduring artifacts ever made by human hands. It simply follows its design, keeps its antenna aligned, and turns fading energy into one more stream of data, one more delayed answer across the dark. On Earth, that answer is received with the same qualities that have sustained the mission for so long: patience, care, and the willingness to value faint things. The signal is weak, the pace is slow, and the future is finite. Yet the connection remains meaningful precisely because it has never been easy. Voyager 1 moves farther into interstellar space, smaller in power each year, but not yet silent. In that continued exchange, there is a calm kind of wonder, not loud, not dramatic, only steady. A machine grows old far from home and still remains in touch. Beyond the sun's outer boundary, beyond the familiar architecture of planets and light, it carries a final lesson in quiet endurance. Distance does not erase meaning when attention is sustained. Weakness does not erase value when truth still returns. And in the dark, a faint signal continues to find its way home.